Okay, this unit is going to focus on some algebra, specifically something called systems of equations, which basically means we're going to be answering questions that involve more than one equation. Okay, so you guys are used to like if I said this, you guys are used to solving equations like this. This is a single equation, get x by itself. Okay. Systems of equations involve more than one variable and more than one equation. So it would be something like this. You don't have to take it down. So we'll talk about them. There's two equations and there's two variables. So solving these involves a little different method. There's actually three different ways we can solve them. Okay, but now see what you're trying to figure out two numbers that add to 10, but also two numbers that when you multiply the first one by 2 and multiply the second one by 2 and add them together, you get 20. Okay, I mean, it is possible to guess and check it. I mean, I could go 5 and 5, but does this work? 5 and 5 is 10, but does 2 times 5 plus 2 times 5 equal 20? Yeah, so that means the answers would be 5 and 5. Okay. There's actually more than one answer in that one, but we'll talk about it later. So anyway, so what we have been studying is something called linear equations. Okay, that's what we've been doing. You guys did it in middle school, and we did it quite a bit in grade 9. We've been doing it this year as well. So a linear equation is an algebraic equation in which the highest degree of the variable is 1. What do I mean by the degree of a variable? Degree of a variable, make sure I get this definition right. Okay. The value of the exponent of a variable. So for example, if I give you this one, two x plus 5 equals 15. Focus on the variable. Okay. What's the value of the exponent of that variable? Well, when we don't write an exponent, what number do we always assume it is? 1. So technically, 2x is the same as 2x to the first. So we would call this degree 1, or a first degree variable. Whenever you guys did Pythagoras, you ended up solving equations that look like this. Okay? This would be a degree 2. Why? Because the exponent has an exponent of 2, or sorry, the variable has an exponent of 2. Okay? We're going to solve a lot more of these next year. You guys can solve some basic ones right now, but we're going to solve a lot more of them next year. So linear equations, we name them by the number of variables of degree 1 in them. So here, notice we have two variables. What's the degree of each variable? Well, 3x is the same as 3x to the first. 2y is the same as 2y to the first. So we would say this is a linear equation because the highest degree is 1 in 2 variables. For the second one, well, we've got 3 variables this time, but each of these variables has an exponent of 1. So we would say this is a linear equation in 3 variables. We're going to focus on these linear equations in 2 variables. And when we have a pair of them, we call this a system of equations. In 2 variables. That's what we're going to focus on. And like the example I gave you at the beginning. So as an example would be, I'll just give you a different example. Let's say we have I'll do this one again. X plus Y is equal to 10, but I'm going to change the second one a little bit. 2x minus 2y is equal to, thank you, is equal to 4. Okay. This one, 5 and 5 are not going to work. Because even though 5 plus 5 is equal to 10, 2 times 5 minus 2 times 5 does not equal 4. So it's got to be a different pair of numbers. And there are ways to figure that out besides just guessing and checking. But what we're going to do just to start is I want to just show you what they look like and what a solution looks like. Okay. So here we have an example. So what's the solution? It's the values of the variable. Sorry, the values of the variable that make both equations true. What does that mean? That means if we substitute the values of the variables in each equation, the left-hand side will equal the right-hand side. So for above, X is going to be 6. Y is going to be 4. That's what it works out to. Why? Because if you substitute 6 for X and 4 for Y into the first equation, 6 plus 4 will equal 10. If you substitute 6 for X and Y for 4 in the second equation, you'll get 12 minus 8, which equals 4. So therefore, X equals 6, Y equals 4 would be the solution to that system of equations. Okay? So right now, we don't know how to solve these things other than just me giving you the answer or guessing and checking. There are ways to do it using algebra. There's actually a way to do it using graphing. Okay? Because notice that these equations have an X and Y in them, which means we can graph them. But for the time being, we're just going to talk about how to verify these things, and we're going to use some actual problems to do that. So all I want to talk about for the remainder of this is going to give you a situation. You're going to have to create 2 equations out of it. Okay? Each situation will have 2 unknowns. You got to create 2 equations out of it. And then I'll tell you what the answer is, and you have to show me it's correct. So a school district has buses that carry 12 passengers, buses that carry 24 passengers. The total passenger capacity for all the buses is 780, and there are 20 more small buses than large buses. Out of all that information, I have to create 2 equations, a system of equations in 2 variables. What are my unknowns, first of all? Sorry? Be more specific. Yes, but what are the unknowns in this question? What am I trying to find? And? How many large buses and how many small buses? Right, so those are the 2 unknowns. The small buses, I don't know how many there are. And the large buses, I don't know how many there are. So we're going to give them variable names, and let's give them X and Y. You could call them S and L if you want. You can give them any name you want. Okay. So from these 2 variables, X and Y, I have to make the 2 equations. So I've got to use this first question, or this part here will give me my first equation. The total passenger capacity is 780. How many people are on each of these? How many are in each of these? And when I combine those, don't I get 780? So therefore, my first equation is going to be 12x. That represents the number of people on the small buses. 24y is going to represent the number of people on the large buses. I don't know how many there are. And when I add them together, I'm going to get the total number of people, which is 780. So that's one equation. The next equation uses this piece of information. There are 20 more small than large. How do I convert that to an equation that uses X and Y? There's actually different answers. I always like to think of, whenever I see this, there are something more than the other, I always write it as a subtraction. Okay? Think of it this way. How many more are there, small or large? Small, right? By how much? 20. So if I take the number of small and subtract the number of large, shouldn't I get 20? If I take the number of small buses, however many there are, and subtract the number of large buses, that should equal 20 because this should be 20 bigger. So that's one way you can write the equation. That's actually a good way to write it when you're solving them. It's not the only way. You could have said, well, the number of small buses will be the number of large buses plus 20, right? Because there's 20 more of these, or sorry, there's 20 more of these, so I got to add 20 to make them equal. So I could have done it that way. I could have said that the number of large buses is going to be the number of small minus 20. So there's actually 3 different ways you could write the equation. All of them are correct. And I would, of course, accept all of them. But I only start with this one because it's easier to solve when they're like this. Okay? Notice that the X's and Y's and the numbers are lined up nicely. We're going to use that to solve these things, one method. Okay, so let's say I told you that there are 35 small and 15 large. How can we determine if this is correct? We got to plug it into these. So we're verifying it. So I am told that X is 35, which means that 12 times 35, large buses is 15, so Y is 15. So 15 times 15, will that work out to a total of 780 people? Notice I put a question mark over it because I'm not sure if it equals yet. I don't know. And not only does it have to satisfy this one, make this one true, does the number of small buses, 35, minus the number of large buses, 15, does that equal 20? Well, that one's kind of obvious, right? Does 35 minus 15 equal 20? Yeah, so that's good. This one we got to do a little bit of work on. So 12 times 35 will give you what? 420? Something's wrong here. That's why it's wrong. Thank you. I knew there was something. Sorry, 420 plus 24 times 15, 360. Does that work out to 780? Yes, because this will add up to 780, which does equal the other side of 780. So just as a conclusion, I can just put verified. Done. Okay. Let's look at another one. The perimeter. Sorry. Yeah. The perimeter of a flag is 16 feet. Its length is 2 feet longer than its width. Out of that, I have to create 2 systems. There will always be 2 unknowns here. What are the unknowns here? Length and width. So let's call the length X, and let's call the width Y. If you want to call them L and W, that's perfectly fine. If you want to call them A and B, that's perfectly fine. So I've got to create 2 equations. One is the information from here. The other is the information from here. You'll always be given enough information in the question to create the equations. So how do I convert this to algebra? Perimeter of the flag is 16 feet, and I'm told that the length is called X and the width is called Y. How do we find the perimeter? We take 2 lengths, we add 2 widths, and that's going to be the perimeter of 16. Excellent. The length is 2 feet longer than the width. So the length is 2 more than the width. Can you try a subtraction? What would you get? What minus what would we do? Length minus width is 2, or width minus length is 2? Which one's bigger? The length. So that means that goes first. So it's going to be X minus Y. The bigger one always is written first. And then you subtract the smaller one, and then it will always equal whatever you're given in the sentence here. Part B is to verify. So we're told the solutions. We are told that the length is 5 and the width is 3. So therefore, does 2 times 5 plus 2 times 3 equals 16? And does 5 minus 3 equal 2? Well, that's kind of an obvious one. That one works. We can check that one. This one we may have to do a little bit of work on. So 2 times 5 is 10, plus 2 times 3 is 6. Does that equal 16? Yes. We don't have to go any further. We know 10 plus 6 is 16. So we are verified. Okay. So hopefully you're getting a little comfortable with this. Let's try another example, because there's all sorts of different situations you can be given. Here we have a school raising $195 by collecting 3,000 items from recycling. They got 5 cents for every pop can, 20 cents for every plastic bottle. What don't I know? The pop cans and the bottles, right? So just to be a little different, I'm going to call the pop can P, pop cans P, and I'm going to call the bottles B. Okay, so the first thing is to identify the 2 unknown variables. Give them lowercase names. Now we got to create the equation. So we got to figure out where in the question is the information to create the 2 equations. Can you tell me one equation? How much? Sorry? P times 5, or in algebra we write 5P plus 20B. Nice. Notice I have to do that because these are in cents. This is in dollars. So you can't say cents plus cents equals dollars. They have to be all cents, or they have to be all in dollar form. So you need to convert to cents by multiplying by 100. So just this here gets you the first equation, which means hopefully you're thinking, this must have to do something with the second. There's 3,000 items. How could you convert that to an equation? Don't overthink. It's actually pretty easy. But I didn't use X and Y. 3 plus B is equal to 3,000. Good. So there's your two equations. Next step, like we've been doing, you're given the answers, you're asked to verify that they're correct. So for part B, I need to know, okay, I'm told that there's 2,700 pop cans, so does 5 times 2,700, 5 cents times 2,700, plus 20 cents times 300, will that work out to 19,500 cents? So that one you're probably going to have to do a little bit of work to show. So 2,700 times 5, 13,500. And this gives us 6,000. Does that work out to 19,500? Well, yeah, when you add these two together, you're going to get 19,500, which does in fact equal 19,500. So the first equation works. Second equation is usually, one of them is usually pretty easy to figure out. Does 2,700 plus 300 equal 3,000? Yeah, it does. Yeah, that's a good one. I can see that. So I'm verified. Good answers. They're correct. Okay, the last example. You're given the problem, you're given the equations, you're told what the answers are. And you're first asked just to verify that they're correct. So a stored display has packages of 8 batteries, E, 4 batteries, F. The total number of 8 batteries in the display was 320. And there were 1.5 times as many packages of 4 batteries as there were 8 batteries. Herman modeled this problem using the system given, and he figured that out by whatever method he used, that he got 30 packages of 8 batteries, 20 packages of 4 batteries. So the first thing we want to do is just verify he's correct, according to what he did. So does 8 times 30 plus 4 times 20, does that work out to 320? Well, that gives me 240 when I multiply those two. That gives me 80 when I multiply those two. Does that work out to 320? Yes, it does. Also, does 1.5 times the 4, 20, will that work out to the number of 30s that he got? So does 1.5 times 20 equal 30? Well, when you do this, you're going to get 30 equals 30. So we verified what he did. The question is, Sherman comes along and says, you're wrong. But Herman says, but I verified it, and it's right. What could potentially be wrong? with Herman. Yes, he got a solution. He got answers that fit these, but maybe he did these wrong in the first place. Right? So if he did these wrong in the first place, he's going to get two answers. And if he checks them, they're going to work. But if they're wrong in the first place, it doesn't matter if they work or not. Can you see one or more of the equations that there's a problem with it, according to what is said here? Does 8 times, would we find the number of batteries by doing the number of 8 packages times 8, the number of 4 packages times 4, and adding them together? That seems right. Like this seems okay. There were 1.5 times as many 4s as 8s. Does that translate to this? This is saying, what is this saying? That there are more 8s or more 4s? Just look at this equation. More 4s? Aren't there more 8s, because don't we have to multiply the 4s to get up to the 8s? So there's more 8s, right? Okay. But yet here he said that there were more 4s. So he's got this wrong. The second equation should be the other way around. It should be 1.5 times the number of 8s will give me up to the number of 4s, because there's more 4s. Okay. So the next step is going to be, great, we know how to set these systems up. We've seen how we can use these systems to help us solve problems. Okay, but you're just telling us the answers. How do we figure out the answers on our own? There's 3 different methods, as I said, and that's basically going to be the rest of Unit 4.